And we also talk about the Linux architecture when used as a router and also as a server. And then we talk about the within Linux kernel, there are actually 4 major components, and networking is just one of the components. So you can count about one-fifth of the kernel, Linux kernel. And within the kernel, you will see the other 4 components and also networking. And within networking, we have hardware-dependent support for drivers, and then hardware-independent. So TCP/IP will be here, and some link layer driver will be here, and then that will be the interface adapters, the interface cards. And then on top, we have application layers, where the client and the server program reside in the user space, out of the kernel space. Okay, for client and server, how do they communicate with each other, passing through the Linux kernel? As we say that client and server are outside the kernel in the user space, and they rely on the Linux kernel to transfer the data between themselves, between each other. So you would need a socket interface called TCP socket or UDP socket. So these are the 2 most common used socket interface for client and server or peer-to-peer. Okay, so usually when you write a client program or a server program, you would use UDP socket or TCP socket. And sometimes you use both. For example, for P2P, you use both. But for some other application or some other tools that you are not interested in talking with the other peer, you are probably interested in getting more information from the kernel. So you would have an interface like a row socket, which enable you to to bypass the TCP UDP layer to access the IP layer. So that's a row socket. Okay. The reason it's called row is because it bypasses TCP and UDP transport layer. And you also have interface which is link layer socket that would enable you to even bypass the IP layer, so that you would access the link layer directly. So when you bypass TCP and IP, then you would have access of the link layer header, for example, Ethernet header or wireless LAN header. Okay. So when do you need this? Okay, when you write a program like Wireshark, which is an open source tool that can sniff and parse the packet detected on the interface card, then you would need to bypass transport layer and IP layer in order to gain access to the Ethernet header or the wireless LAN headers. Okay. And some applications do need to bypass TCP, but do not need to bypass IP layer. For example, a tool called trace path or trace route. They need to access the IP header by setting the TTL field in the IP header. Then it would need to access the IP layer directly. Okay. And there's another interface called routing socket that would enable you to access the kernel structures. Remember that the reason why it's called routing socket is apparent, because it's when it was designed, it's mainly to access the routing table within the kernel. Remember last week we talked about why we put the routing daemon, which does the calculation in a daemon. However, the routing table itself is in the kernel. So there must be an interface allowing the daemon, the routing daemon, to access, to update the routing table in the kernel. And routing socket is for that purpose. So these socket interface are there for programmers, for developers to access, either through the peer on the network or to access the kernel. Okay, so next let's look at the driver. Within the kernel, there's a piece of software that knows the hardware pretty well. So the driver is managed to access the hardware, and it needs to know everything about the hardware. I mean, not everything, but basically how to interact with the hardware. Usually on the hardware, there are several things. One is the register and the buffer and also DMA. These are visible to the driver. And these are the interface for the driver to access. However, there are some other stuff, but not visible to the driver. So why does the driver need to know this? Because the driver will issue command to the interface card, and also read the status from the interface card. And for those command and status, they are stored in the registers. So the register here are visible for the driver to read and write. You write command and read status about the interface card. So let's look at the two flows. One is the transmission and one is reception. When transmitting a packet, when you write a driver for transmission, you need to separate into two parts. One part is active part, and the other part will be passive, driven by interrupt. So when you transmit a packet, you issue you pass the packet and also issue command. You call this module, and then the transmission here in the driver will then write commands into the register. Okay, and then the hardware, on the adapter card will do the job to do depending on the command, it would do the job. And usually when you want to transmit a packet, you tell the interface card, okay, I'm going to send a packet, and the packet is right now in the main memory, and you need to copy the packet from the main memory to the interface card by DMA. So after receiving this command, the hardware, the interface card, the DMA would do the job to copy the packet from the main memory on the motherboard to the interface card. Okay, it would do the copy without CPU involvement. So CPU, when executing the instruction here, would just fill the command into the register, and then it's done. Then it's DMA's job to do the actual packet moving. And when done, when the moving packet copy is done, then the interface card will generate an interrupt. And then CPU will be interrupted and then pass the control to the driver. Okay. And then it will come here. It would then read the register to see, okay, what happened. So the driver will read the register to know that, okay, you have finished copying the packet and transmitting the packet. So actually, after finish the copy the packet, the interface card will do the job to transmit the packet. And when copy and transmission are finished, it would interrupt the CPU. And then when driver gain the CPU control and read the register, it would find that the packet has been transmitted, say, successfully. Then probably if there's a queue of packets, then it would issue another command asking the driver to copy another packet and then transmit the packet. So by this, maybe the first packet will be active in transmit by this module, and subsequent packet will then driven by interrupt and then transmitted by this module in the driver. So actually, there's a better interface. You will immediately see that you would have per packet interrupt. In order to transmit a packet, say I want to transmit 10 packets, then I will get 10 interrupts. But there are better ways without so many interrupts in the new API, of Linux, for Linux. And chapter 3 has a section on that device driver. So we'll talk about that in chapter 3. And then how about the receiving part? Okay, the receiving part in the driver is totally interrupt driven, meaning if there's a packet received by the interface card, then the interface card will interrupt the CPU, and the control will be passed to the driver here, and then it would read the register to see, okay, what happened, and now after reading the register, the driver understands, okay, there's a packet coming in, and I need to tell the interface card where to copy the packet to, because the packet is now in the interface card mem buffer, and it needs to be copied to the memory. So I issue a command to the register telling the interface card the address in the memory, which is used to store the packets. So I issue a command telling the interface card to copy the address of the memory where the interface card can copy the packet to. So then I'm done. And then the DMA would do the job to copy the packet from the interface card to the memory. Once done, it generates another interrupt telling the driver, okay, I'm done. The packet is there at the address you have specified. And next, the driver can inspect the packet and process the packet. So as you can see that the driver work in this fashion. Some part is not interrupt driven, active part. But the other part are interrupt driven. So you need to work along with interrupt. And you need to understand, the driver needs to understand the registers on the interface card, which is specified in a document often called data sheet of the interface card. So when you write a driver, you need to know this, and then you know how to program, rewrite the register, issue command, and read the status. So that's the idea of the driver. And data sheet usually capture an array, describe an array of registers, and by reading data sheet, you will know how to program. Okay. Any question on the open source implementation so far? So one thing you might ask is, we mentioned that the TCP/IP is in the kernel, and the application layer is in the user space, and the link layer How about the link layer? Is it in the driver or in the interface card? Is it in the driver or in the interface card? For example, the wireless LAN is a link protocol, or the Ethernet is a link layer protocol. Is it in the driver or in the interface card? Is it in the software or in the hardware? Or say PPP. PPP is another protocol, link layer protocol. Is it in the driver or interface card? So it's a question of whether to put the link layer in a software or in a hardware. And the answer lies in whether the protocol operation is time sensitive. If the operation is time sensitive, meaning it needs to be fast enough, it has many timing constraints in the operation. Say, I need to send this packet within how many microseconds, or I need to send this packet in how many nanoseconds. So then it is time sensitive, then it will be put into the hardware. However, if the operation of the protocol is not that time critical to, say, microsecond scale or even nanosecond scale, then it could be implemented in software, okay, for better flexibility. So with this idea or this principle in mind, then you will see that because in Ethernet, the protocol is time sensitive, so it will be put into the hardware. And so is the wireless LAN protocol, which is very time sensitive. And we will talk about those operations in chapter 3. And they are indeed time sensitive with many time constraints. So they are put into the hardware. But PPP is a point-to-point protocol that you probably use every day at home if you connect to the internet by DSL, by ADSL. You are actually riding on top of PPP. However, PPP operation is not time sensitive, not time critical, so they are not put into the hardware. They could be put into the driver, solely in the driver. So the entire PPP implementation is in the driver, not in the hardware. Okay, then how about if Ethernet and wireless LAN protocols are implemented in the hardware, the interface card, then what does the driver for Ethernet and wireless LAN do? What do they do? What do the driver for Ethernet and wireless LAN do? Basically, they just copy packets in and out. So in that case, the driver does not implement protocols. Say PPP is here in the driver, but Ethernet and wireless LAN is here. But how about we do have driver for Ethernet and wireless LAN? And what do the drivers do? They do copy, memory packet copy, going out from the main memory to the interface card, and also from the interface card to the main memory by DMA. So we need to work with interrupt and DMA to copy the packet in and out, and that's the driver's job when you are having the link layer implemented solely in hardware. Then you still need a driver to do the packet copy. Okay, any questions on the open source implementation?